Humanity's fascination with the cosmos stretches back through time, from ancient mythologies to modern scientific inquiry. Ancient civilizations envisioned worlds beyond their own. Hidden realms, parallel heavens, and infinite stars scattered across the heavens. In Hindu cosmology, the universe was imagined as an eternal cycle of creation and destruction, an endless dance that existed beyond the human understanding of time. Meanwhile, Greek philosophers like Democritus speculated on the existence of infinite worlds, some similar to ours, others completely alien in nature. The idea that we might not be alone, that our universe might not be the only one, existed in these ancient minds long before science dared entertain it. Today, these ancient stories no longer sound like myth, but like the early inklings of a concept that modern physicists are now seriously considering: the multiverse. The idea that we might live in just one universe among an endless array of others has shifted from the realm of speculative fiction to a real scientific possibility. For much of human history, we thought of the cosmos as a single, vast, and self-contained expanse with Earth at its center. But then came Copernicus, who boldly shifted our view by placing the sun at the center of the universe. Later, Edwin Hubble's observations revealed that the Milky Way was not the entirety of the universe. There were galaxies beyond our own, spreading outward, each containing billions of stars. This constant unveiling of greater and greater expanses, once thought unimaginable, opened the door to ideas that pushed the limits of what we thought we knew about the universe. And just when scientists thought they had mapped the farthest reaches of space, another possibility emerged. The universe we see might be just one layer in a vast, intricate multiverse, each layer more expansive and stranger than the last. Max Tegmark, a young boy growing up in Sweden, was no stranger to these grand ideas. His father, Harold, a mathematician, believed that everything, from the formation of snowflakes to the arrangement of galaxies, could be understood if you found the right equation. His mother, Karen, was an artist, filled with wonder and beauty, often seeing patterns in brush strokes the same way Harold saw them in data. From them, Max inherited both the precision of mathematics and the boundless wonder of art. Growing up in the Tegmark home, Max's dinner conversations often shifted between abstract mathematical proofs and deep philosophical debates about existence. This duality of thought led Max to a profound conclusion. What if mathematics wasn't just a tool to measure the universe? What if math was the very structure of reality itself? This notion became his obsession, driving him to see equations not as dry formulas, but as living structures, almost like works of art that shape the world around him. At school, Max stood out. While his classmates rushed to finish their math assignments, he lingered on the deeper questions behind the numbers, always asking why math worked so perfectly, so universally. Teachers saw him as brilliant, but distracted, a dreamer who saw the hidden beauty in equations while others simply sought solutions. By the time he reached university, that quiet conviction had turned into a theory. The universe itself might be mathematical. His work, blending the hard logic of mathematics with unsettling questions about existence, eventually drew the attention of physicists at the Massachusetts Institute of Technology, MIT, where he continued to build on this idea. While other physicists focused on unifying quantum theory and general relativity, Max returned to his childhood question: what if the universe itself is made of mathematics? From this seed grew one of the boldest ideas in modern science, one that would take the world of physics and cosmology by storm. In the early 20th century, a breakthrough moment came. Edwin Hubble, perched at the summit of Mount Wilson in California, used the powerful Hooker telescope to peer into the night sky, unraveling a mystery that had lingered for centuries. At the time, astronomers had long debated the nature of the faint, cloudy smudges scattered across the sky. Some believed they were part of our own galaxy, the Milky Way, while others argued they were distant, separate galaxies. The scientific community was divided, with no solid evidence to support either side. But Hubble, armed with the most powerful telescope in the world, set out to end the debate for good. Through painstaking observation, Hubble discovered that the Andromeda Nebula, a smudge in the sky, was actually a galaxy far beyond our own, millions of light-years away. The revelation shattered the belief that the Milky Way was the only galaxy, effectively proving that our universe was far more vast than anyone had imagined. It was a discovery that forever changed the way we viewed the cosmos. But Hubble's work didn't stop there. His subsequent discovery of redshifts, galaxies moving away from us at an accelerating rate, led to the realization that the universe was not only vast, but expanding. This was the breakthrough that confirmed the universe had a beginning, the Big Bang. Yet, the Big Bang theory, despite its evidence, was controversial. Many scientists resisted the idea that the universe had a beginning. The steady-state theory, proposed by Fred Hoyle, argued that the universe was eternal and unchanging, constantly forming new matter to fill the gaps as it expanded. But the evidence, Hubble's redshift, the discovery of the cosmic microwave background radiation, continued to build the case for a universe born in a fiery explosion. In 1965, Arno Penzias and Robert Wilson at Bell Labs accidentally discovered the cosmic microwave background radiation while working on an unrelated project. This faint, persistent noise was the afterglow of the Big Bang, a remnant of the universe's earliest moments. The discovery confirmed the Big Bang theory, providing the smoking gun that scientists had been searching for. But even as the evidence for the Big Bang mounted, a new problem emerged. The cosmic microwave background radiation was astonishingly smooth. If the universe had exploded from a single point, how could regions of space that were never in contact have the same temperature? This became known as the horizon problem, and it posed a significant challenge to the Big Bang theory. In 1979, physicist Alan Guth, while struggling with the same problems, proposed a bold solution: cosmic inflation. He suggested that in the earliest moments after the Big Bang, the universe underwent an exponentially rapid expansion, expanding faster than the speed of light. This inflationary period would have allowed distant regions of space to come into contact with one another, evening out the temperature across the universe and solving the horizon problem. It also provided an explanation for the flatness of the universe and the absence of magnetic monopoles, particles predicted by physics but never observed in nature. Inflation theory was a radical departure from the Big Bang model, but it provided a simple and elegant solution to several problems in cosmology. Guth's model explained how the universe could appear so smooth and uniform, even though distant regions of space had never been in contact. It also offered a mechanism for the creation of the cosmic structures we see today, galaxies, clusters, and superclusters, by stretching quantum fluctuations into the vast cosmic structures we observe. But even as inflation theory gained acceptance, a new possibility emerged, one that would stretch the imagination even further. What if the universe we observe is not the only one? What if there are countless other universes, each one distinct from our own, governed by different laws of physics? This idea, once dismissed as pure speculation, began to gain traction among cosmologists. Max Tegmark, who had already become fascinated with the implications of a mathematical universe, saw an opportunity to build on the foundations of inflation theory. What if the entire universe, everything from particles to galaxies, from time to space, was not just described by mathematics but was itself a mathematical structure? This radical idea would become known as the mathematical universe hypothesis. Tegmark proposed that the universe isn't made of matter, energy, or even space-time. It is made of mathematics itself. In this framework, every mathematical structure that is consistent with the laws of physics exists as a real, separate universe. Our universe, with its 3 spatial dimensions and 1 of time, is just one of many possible mathematical structures. There could be universes with more or fewer dimensions, universes governed by different physical constants, and even universes where the rules of logic itself are different. The idea of a multiverse, in which infinite universes exist alongside our own, each one with its own set of laws, was groundbreaking. And it came with profound philosophical implications. If mathematics is the foundation of all reality, then the universe we see is just one solution to the ultimate equation. Every possibility, every potential outcome, exists somewhere in this vast, infinite expanse of reality. As the concept of the multiverse began to gain momentum, it faced both scientific and philosophical challenges. The idea of infinite universes, each with its own set of rules, seemed impossible to test or observe. Some physicists argued that the multiverse was untestable and thus unscientific. Others, like Tegmark, embraced the idea that the multiverse was the natural consequence of an infinite cosmos, a logical extension of the principles of inflation and quantum mechanics. Tegmark's vision expanded on Everett's many-worlds hypothesis, which proposed that every possible quantum outcome exists in a separate, parallel universe. But where Everett saw branching realities, Tegmark saw a landscape of infinite possibilities. Each mathematical structure, each set of physical laws, was a universe in itself, existing alongside countless others. This vision of an infinite, mathematically structured multiverse, with its layers of parallel universes and infinite possibilities, opened up a world of philosophical and scientific questions. If every mathematical structure exists as a universe, then what does that say about the nature of reality itself? What are the implications for the laws of physics, for our understanding of time and space, and for our place in the cosmos? As we continue to explore the mysteries of the universe, we are confronted with the possibility that the cosmos is far more complex than we ever imagined. The idea of a multiverse, once confined to science fiction, is now a serious scientific theory, one that challenges our understanding of existence, reality, and the very nature of the universe. The future of cosmology may be one of endless discovery, as we venture deeper into the mathematical fabric of the cosmos and uncover the infinite possibilities that lie beyond. As we continue our journey through the vast, unfathomable expanse of the cosmos, one question keeps echoing in our minds. What if our universe is just one of many, one of countless worlds, each governed by its own unique laws and rules? Could there truly be infinite realities, all existing side by side, each one as real as the next? It's a question that challenges not just our understanding of the universe, but the very nature of existence itself. To understand this, we must first explore the origins of the concept of a multiverse and how it evolved into one of the most profound ideas in modern physics. The multiverse theory, though radical, did not emerge out of nowhere. Its roots can be traced back to some of the earliest developments in cosmology. In the 1920s, Edwin Hubble's discovery that our galaxy was not the only galaxy, but part of a vast and expanding universe, shattered the long-held belief that the Milky Way was the entirety of existence. This revelation, though mind-boggling, opened the door to the possibility that the universe was far more complex than anyone had imagined. The expansion of space, as Hubble's data showed, was not just a local phenomenon. The universe itself was stretching, and galaxies were receding from each other like dots on the surface of an inflating balloon. This was the first inkling that the cosmos was not static, but dynamic and ever-changing. However, this discovery didn't just open the door to new ideas. It also forced scientists to confront even bigger questions. If the universe was expanding, what was the origin of this expansion? Was the universe eternal, or did it have a beginning? The answer, in the form of the Big Bang theory, came to dominate the scientific community in the mid-20th century. According to this theory, the universe began as an infinitely dense point roughly 13.8 billion years ago, and it has been expanding ever since. But even as the Big Bang theory gained traction, another problem emerged: the horizon problem. The cosmic microwave background radiation, which is the faint afterglow of the Big Bang, showed the universe to be astonishingly smooth, with temperatures that were almost perfectly uniform across vast distances. However, if the universe had begun in a hot explosion, how could regions of space so far apart have come to the same temperature? The answer, it seemed, lay in a radical new theory that emerged in the late 1970s: cosmic inflation. Alan Guth, a physicist working at MIT, proposed the theory of inflation to solve the horizon problem. He suggested that, in the very first moments after the Big Bang, the universe underwent an exponentially rapid expansion, much faster than the speed of light. This sudden, explosive growth allowed distant regions of space to come into contact with each other, evening out the temperature and creating the smooth universe we observe today. Inflation theory also provided a mechanism for the formation of galaxies, clusters, and superclusters, explaining the large-scale structure of the universe. Cosmic inflation was a revolutionary idea. It not only solved the horizon problem but also explained the uniformity of the universe and the formation of its intricate structures. But as scientists began to consider the implications of inflation, they realized that the theory suggested something far more radical. If inflation continued forever, it would create an infinite number of separate, non-interacting universes, each one forming its own distinct space-time bubble. This idea, known as eternal inflation, introduced the possibility of a vast multiverse, an infinite number of universes, each with its own set of physical laws and constants. The multiverse theory was a natural outgrowth of inflation, but it was also deeply unsettling. If there were an infinite number of universes, each with different physical laws, how could we possibly know anything about the one we inhabit? The very idea of a multiverse seemed to undermine the uniqueness of our existence and raise profound questions about the nature of reality itself. Max Tegmark, a physicist at MIT, was one of the first to embrace the idea of a multiverse as a way to make sense of the strange and seemingly random features of our universe. Building on the work of other scientists, Tegmark proposed a four-level hierarchy of multiverses, each one stranger and more radical than the last. His framework sought to categorize the different types of multiverses that could exist, based on their underlying physical laws and structures. At the first level, Tegmark's multiverse is a simple, infinite universe where everything that can happen eventually does. Imagine flipping a coin 100 times. In our universe, you might get a particular sequence of heads and tails. But in an infinite universe, every possible sequence of flips exists somewhere, far beyond our reach. In this way, every possibility is realized in some corner of the cosmos. The universe might seem vast, but in the realm of infinite possibilities, it's just a small slice of a much larger whole. Tegmark's second level introduces the concept of bubble universes, each one born from a separate inflationary region. These bubbles are isolated from one another, each one containing its own distinct laws of physics. In one bubble, gravity might be stronger. In another, the laws of chemistry could be completely different. While these universes are born from the same basic inflationary process, they are fundamentally distinct, each one with its own set of physical constants. The third level, which Tegmark calls the quantum multiverse, is perhaps the most radical. Based on Hugh Everett's many worlds interpretation of quantum mechanics, this level proposes that every quantum decision creates a new branch of reality. In one world, you choose one path. In another, you choose a different one. Every possible outcome of every quantum event exists in a separate parallel universe. This idea, once dismissed as science fiction, is now a serious contender in the search for a deeper understanding of reality. But it is the fourth level of Tegmark's multiverse that truly stretches the imagination. At this level, mathematics itself becomes the foundation of reality. Tegmark proposes that every possible mathematical structure exists as a real universe, each one governed by its own set of rules and laws. Our universe, with its 3 dimensions of space and one of time, is just one mathematical structure among countless others. In other universes, there could be more dimensions or completely different laws of physics, or even entirely different kinds of mathematical logic. The universe, in this view, is not made of particles, energy, or matter. It is made of mathematics itself. This fourth level of the multiverse introduces a radical new way of thinking about existence. If reality is mathematical, then it follows that everything in the universe, everything from the smallest particle to the largest galaxy, is just one solution to an ultimate equation. And if that equation can describe every possible universe, then the number of universes is not just large, it is infinite. This idea raises profound questions about the nature of reality, the existence of other forms of life, and the limits of human knowledge. Could we ever comprehend the full extent of the multiverse? Or are we simply trapped within the boundaries of our own bubble universe, unable to reach beyond the horizon? As we explore the implications of Tegmark's multiverse, we begin to confront the deepest questions of existence. What is the nature of reality? Are we just one small part of an infinite cosmic tapestry? If there are infinite universes, each with its own laws of physics, what does that say about our place in the cosmos? And perhaps most importantly, if reality is truly mathematical, what does that mean for the future of science and our ability to understand the universe? The answers to these questions may be far beyond our reach, but the search for them is one of the most exciting and profound quests in modern science. Whether we are on the edge of a new understanding of the universe or simply scratching the surface, one thing is certain: the exploration of the multiverse is only just beginning, and the possibilities, like the universe itself, are infinite. As we delve deeper into the cosmos and the potential for a multiverse, we face questions that are as mind-bending as they are fundamental. What if the universe we know, the one we see, touch, and feel, is just a tiny part of a much grander cosmic structure? A single bubble within an infinite sea of universes, each with its own unique set of laws, constants, and possibilities. Could there really be infinite realities, each one subtly or radically different from the next? And, perhaps more intriguingly, what happens when the boundaries of physics themselves start to dissolve, revealing an even deeper layer of existence? The idea of a multiverse has always been controversial, even as evidence for its existence continues to mount. For many, the multiverse represents the final frontier of speculative physics, an idea that, while fascinating, may be too far beyond the scope of our current scientific understanding to test or prove. Yet, despite the challenges, the multiverse theory has evolved into one of the most profound ideas in modern cosmology, pushing the boundaries of what we know about space, time, and reality itself. Max Tegmark, the physicist who proposed the radical idea of a mathematical universe, takes the concept of the multiverse to its most extreme conclusion. The multiverse is not just a collection of different universes, but a complete and total mathematical landscape where every possible mathematical structure is an actual real universe. In this view, the universe we inhabit is not made of particles or energy or even space-time. It is made of mathematics itself. The laws of physics that govern our universe are simply one set of equations in an infinite, ever-expanding field of mathematical possibilities. This idea of a mathematical universe opens up new avenues of thought about the nature of existence. If mathematics is the fundamental building block of reality, then the possibilities are endless. Universes with more dimensions, or entirely different forms of geometry, could exist just beyond our comprehension. Some universes might have no time at all, while others could have an infinite number of timelines, each one unfolding according to different rules. The very fabric of reality, it seems, may be far more complex than we can even begin to grasp. Yet, as we explore these profound questions, we find that we are not alone in considering the implications of the multiverse. Other physicists and cosmologists, though working from different perspectives, have arrived at similar conclusions. The idea that there could be many universes, each with its own distinct physical laws, has been proposed by various schools of thought. Andre Linde's theory of eternal inflation suggests that the universe we observe is just one bubble in an infinitely inflating sea of bubbles, each one representing a different universe with its own set of physical laws. Similarly, the work of Leonard Susskind and Gerard T. Hooft on string theory and the holographic principle points to the possibility that our universe could be a projection of information encoded on a lower-dimensional surface, with a vast number of other universes coexisting alongside it. Yet, all of these ideas remain speculative, unable to be tested or proven with our current scientific tools. For many, this leaves the multiverse as little more than a fascinating idea, an abstract concept that stretches the imagination but eludes the grasp of empirical science. And yet, as the work of physicists like Tegmark and Linde continues to push the boundaries of our understanding, the notion of a multiverse begins to take on a new form, one that feels increasingly grounded in the fabric of modern physics. It is here, in the realm of quantum mechanics, that the multiverse theory intersects with one of the most profound questions in all of physics: the nature of quantum reality. Since the early 20th century, quantum mechanics has challenged our understanding of the physical world, revealing a realm of strange, probabilistic behavior that defies the deterministic laws of classical physics. In the quantum world, particles can exist in multiple states at once, and the act of observation itself seems to influence the outcome of events. This strange behavior gave rise to the many-worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. Everett's radical idea was that instead of the wave function collapsing into a single state when an observation is made, all possible outcomes of a quantum event exist simultaneously in separate, non-interacting branches of reality. In this view, every quantum decision, every measurement, creates a new universe, each one playing out a different possibility. This idea, once dismissed as science fiction, has gained increasing acceptance in the years since, particularly with the advent of modern quantum theory and the concept of quantum decoherence. Quantum decoherence, as explained by physicists like Wycheck-Zurek, provides a mechanism for the branching of realities. When a quantum system interacts with its environment, whether through light, particles, or even a measuring device, the wave function no longer remains in superposition. Instead, it splits into separate, non-interacting branches, each representing a different outcome. This provides a way to understand how the seemingly strange behavior of quantum particles could lead to a multiverse of branching realities. But while the many-worlds interpretation offers a compelling framework for understanding the quantum multiverse, it also raises profound questions about the nature of reality itself. If every possible outcome of every quantum event exists in a separate universe, then does this mean that every decision, every action, every possibility is realized somewhere in the vastness of the multiverse? Are we, in a sense, living in a cosmic choose-your-own-adventure story, with countless versions of ourselves existing in parallel worlds, each one living a different version of our lives? The implications of this idea are staggering. Imagine that every choice you've ever made, the paths you've taken, the people you've met, the decisions you've faced, exists not just as a memory, but as a living, breathing reality in another universe. In one version of yourself, you took the job you turned down. In another, you married the person you never met. In yet another, you chose a completely different path, one you may have never even considered. The number of possibilities is infinite, stretching out across the multiverse in ways that are both beautiful and unsettling. And yet, as Max Tegmark's mathematical universe hypothesis suggests, the multiverse does not just consist of universes with different physical laws or quantum decisions. It is a vast landscape of mathematical structures, each one a unique expression of mathematical reality. Our universe, with its 3 dimensions of space and 1 of time, is just one of countless possible mathematical structures. There could be universes with more dimensions, or entirely different laws of physics, or even universes where the very fabric of logic is different. This brings us to a final, profound question. If the multiverse exists, what is its true nature? Are we simply one bubble in an infinite sea of universes, each one governed by different laws? Or is the multiverse a vast and intricate landscape of mathematical structures, each one playing out its own cosmic drama? And if mathematics is the foundation of all reality, as Tegmark suggests, then how many other mathematical structures exist, waiting to be discovered? As we ponder these questions, one thing becomes clear. The universe, in all its complexity and wonder, is far stranger than we could have ever imagined. The multiverse, with its infinite possibilities, offers a tantalizing glimpse into the deeper structure of reality. And while we may never be able to test these ideas directly, they challenge us to think beyond the limits of our own universe, to imagine a reality that stretches far beyond the horizon of our understanding. So, as we reach the end of this journey, we are left with a profound realization. The universe is not just a single, finite expanse of space and time. It is a vast, infinite, and ever-expanding landscape, one that may contain infinite versions of ourselves, infinite possibilities, and infinite universes, each governed by its own set of mathematical laws. The multiverse, in all its grandeur, is not just a possibility. It is a reality waiting to be understood. And as we continue to push the boundaries of our knowledge, we may one day uncover the deepest secrets of existence, and perhaps catch a glimpse of the infinite beyond.